I think we can get started now, although there might be one or two stragglers. I'd like to welcome you. I'm Marlene Lockheed, a member of the board of the Princeton Adult School, and it's my pleasure to introduce tonight's speaker. But right now, a bit of housekeeping. First, congratulations to all of you who found your way to this new venue. You get high marks for navigation. Second, if you've not received an invitation to the Princeton Adult School's Gala on May 4th, please let me or any other member of the board know. We'll make sure we have some here tonight, and we'll make sure you get one. And for those of you who've already received invitations, please do plan on attending. It should be great fun. And now on with the show. Tonight's speaker is Michael G. Littman, a professor of mechanical and aerospace engineering at Princeton and a scientist with a wide range of interests. Much to my surprise, as a Lockheed, he does not design airplanes. He holds a PhD in physics from MIT, as well as a summa cum laude BA from Brandeis, and is an experimentalist in optics and spectroscopy, which I can't pronounce, and is helping to design telescopes that would allow for optical imaging of Earth-like planets around nearby stars, according to his resume. Professor Littman is a fellow of the Optical Society of America, a recipient of its 2005 Engineering Excellence Award for, and I quote, "the grazing incidence turnable laser and subsequent improvements, including a geometrical scanning mechanism that allows for continuous single-mode tuning with one moving element." He also holds patents for multi-mode reconfigurable pipeline computer and a thermal pattern generator for pain control, which sounds like a good idea. Professor Littman is also an honorary life member of the Franklin Institute and has designed exhibits for its Science Museum, one for a computerized model railroad and another for an exhibit about the brain. For the past few years, he's been studying the history of modern engineering, including science and innovations in New Jersey, and fortunately for us, this history, rather than his basic scientific research, will be the subject of tonight's talk. Please join with me in welcoming Professor Michael Littman, who will address us tonight on the topic of Princeton innovations in service to society, transistor, computer, and internet.
Thanks so much. Let's see, I've got to get my microphone back on. So it's my pleasure to be here. I teach a course on feedback. That's feedback. Okay. A little lower, please. Great. I think we're okay. Good. Thank you. So that's actually my tunable laser that I designed years ago is based on regenerative feedback. So that's exactly this effect. So let's see. The microphone's pointing near the speakers is when we have a problem. I'm pleased to put together this talk. I teach a course on the history of engineering, and this talk is actually an excerpted from 3 of the lectures. One on radio, one on the transistor and the microchip, and another one on the history of computers. And I want to spend a few minutes to go through the opening slide here to sort of set the stage for what I have to say. So first off, let's see, the 3 important ideas are, this is Princeton, as in Princeton University, the town of Princeton. It also includes the Institute for Advanced Studies. And there are 3 important innovations. Oh yes, this whole seminar series is 75 years, at least in 75 years. It's 1939 to 2014. And the 3 objects that I want to focus in on are the transistor, the computer, and the internet. And each one of these objects has a very strong Princeton association. The strongest, though, is with the computer. So the computers that we use today are known as the Princeton architecture. Sometimes it's known as the von Neumann architecture, named after John von Neumann. who was a professor of mathematics here and was also at the Institute for Advanced Study. So we'll get to that story in the middle. The transistor is this very important object that was invented in about 1948. So it's within this period of 75 years, and it's the building block of modern computers and the internet. And we're going to see that one of the prime movers in that is John Bardeen. So John Bardeen was a student of Eugene Wigner's, products of our physics department. Then he went off to Bell Labs as a solid-state physicist and got his first Nobel Prize for the transistor. He got a second one for superconductivity, the BCS theory. And then Bardeen is the scientist. Von Neumann is the mathematician. And then Robert Kahn is a graduate of our electrical engineering department. He was a PhD student here. And then he went off to work with Bolt, Beranek, and Newman in the Boston area. And he is one of the co-founders of the Internet Protocol. So these are three important people, all connected with Princeton. And I'm going to focus in on these three individuals. Notice that I picked this cover slide off of the ones that I used that I lecture with. And this is for the students' use. It says computers are allowed to notate only, right? And please no texting and internet use. So the reason for the computer, as you know, the college students today, they tend to open up their computers and lecture. And in terms of service to society, this is something where I think that these three objects, the transistor, the computer, and the internet, maybe are not. Oh, let me first also the subtitle. I forgot before I go to the next slide. So the course that I do on the history of engineering deals with all of engineering. And we define all of engineering through examples. And the examples are structures, machines, networks, and processes. And if you think of those four topics, structures is civil engineering, machines is mechanical engineering, networks is electrical engineering, and processes is chemical engineering. It's the usual way to think of it. Now, in the case of a computer, I'm going to be talking about the transistor, which is an element for a computer. And it's the structure. We talk about computer architecture. So think of designing the computer. That's the architecture. The processing, where chemical engineers deal with the processing of materials, for example, oil, the refining of oil. Here we're going to be processing data. And of course, we think of the computer, even though it's an electronic object, we think of it as a machine for manipulating data. And it's also the network is the idea of the internet. This is the computer network. And I also like the idea of scientific social symbolic. This is also something that we do in our course, to deal with the perspective, to look at engineering works. And so on the technical side, computation. So these are going to be objects that we can use for computation. On the social side, if you think about the role of computers, you can think about their role in communication and commerce. So that's when you network computers together. And then on the symbolic side, I'm going to bring out the symbolism associated with the computer and the internet. The main thing, let's think of artificial intelligence as a symbolic idea. Now, as I was saying, our students have this tendency to use their computers in lecture, and this is a transformation of the society that perhaps is not so good. This is what happens to lecture halls. So this, I picked this picture up. There's a lecture going on in this image. You'll see there's a picture on the screen. And if you scan the computers that are in the audience there, you'll see that I think only 3 of the computers are actually pointing to the lecture. The others, I think, are involved in computation, communication, and commerce. There's at least one that's shopping. I think that there's another one, several others are doing their email. And then perhaps somebody is balancing their checkbook. I don't know. By the way, I lifted that image off of a site that was talking about the modern classroom, and they wired up a student to a sensor and saw how much activity they had for different times in their day. The boxes there, the upper box there is television, so you see it's a very low level of activity. Sleep, as it turns out, has a lot of activity, which is very interesting. Relaxation, low level. Study, there's lots of activity, but the one at the bottom right there is when they're in class. They're out in the cold. Okay, Okay, and then before I get started with my materials, I borrowed a few ideas, general ideas for this lecture and in general. One, I don't know if you know of this series of public broadcasting, PBS, called Connections, James Burke. It was around about 15, 20 years ago. There's a series of books that went with it. And James Burke, you can't read the text there, but it says Connections. It says from Ptolemy's astrolabe to the discovery of electricity, how inventions are linked and how they cause change throughout history. So that idea of how inventions are linked and change are themes that I resonate with. So that's one idea. And then the other one is an idea that I first heard about through Newton, which is the idea that Newton was asked of how he could see further than others, and he says it's because he stood on the shoulders of giants. When I researched it for a good image for this lecture, I found out that he lifted that from someone else in the 12th century. So there's an image from the 12th century of a giant and somebody standing on his shoulders, and that idea of seeing further is on the shoulders of giants, because the giants are going to be giants, not just the people that I'm going to talk about today, but the people that they drew upon. So let's start with our ideas. So let me start off with the transistor. Now, this is not going to be a very technical talk, but there are going to be some technical ideas. And I want to start off with what is a transistor. And so I have a list of questions here. The most important idea is thinking of it as a valve for electrical current. So when I say a valve, it has the ability to pass current or restrict current. Okay? It doesn't generate current. It's just, as a matter of fact, the name transistor is called transfer resistor. It has a resistance that you can modify. So it's a tiny valve that controls current, and it is controlled by current. See that in a minute. The key people that I'm going to focus in on, as I mentioned, is Bardini and Breton and Shockley. These are the three of them were at Bell Labs. Bardini is the scientist, Breton is the engineer, and Shockley is the manager. And the three of them shared the Nobel Prize for the transistor. Then, in terms of how it's used. So it's used as an amplifier. I'm going to try to explain to you precisely what I mean when I say it's used as an amplifier. It's also used in digital logic. So this is switching logic that computers are based on. And it's also used in digital memory. And I will give you a little example of a digital memory, a flip-flop, in a little bit. I want to also like to look at its origins. And the origins are the electromagnetic relay, which has a very strong connection with Princeton. The electromagnetic relay was invented in 1831 by Professor Joseph Henry, who was a professor here. You may know of the Joseph Henry House. Actually, he came to Princeton in 1832. His first form was 31. A later form is 35. That house was a little bit later, so there's two houses that were later. But it was that the relay was invented here in Princeton. The transistor also has its origin to the crystal diode, which preceded the vacuum triode. And we'll look at these objects in a little bit. And then the significance of the transistor is that it's a very small, rugged device. It's a switch. And it has the property, because it's so small, it has a small capacitance, which means its switching time is very fast. And so it allowed you to make, it allowed the modern microelectronics generation. So you can get 1 million transistors on a little chip, because they're so small, and they're also very quick, so it allows us to have computer clocking times of 1 billion times a second. And it integrates together into these very complex circuits. Okay, so the valve there, of course, is just a valve for water, and down below is the symbol of a transistor. Now, I like this image. I use this a lot in my courses. This is an image that was at the end of the 20th century by Edward Sorel. It was 20 important Americans that contributed to progress. It was modeled on Christian Schussele's image called Men of Progress. You can see it's called People of Progress, so we made progress in 100 years, going from the 19th century to the 20th century. And the people that I highlight there are those that are related to today's lecture. So the one on the right there holding a little microchip is Robert Noyce. He's the founder of Intel Corporation. The microchip is one of the two key people in the microchip. There's Edwin Armstrong. He was a professor of electrical engineering and the developer of FM, frequency modulated radio, and other radio circuits at Columbia University. In the middle there you see John von Neumann, and he's writing out an equation showing you that he's a mathematician. And looking over his shoulder, he's probably trying to steal an idea from him, is Bill Gates. So gazing over with an interesting glare in his eye. And then we have Licklider. Licklider was with ARPA. He was one of the individuals that imagined the internet. So these are 5 of these 20 people are all connected with today's story. So here's Edwin Armstrong, a stamp. I like to use a lot of stamps. It identifies the importance of some of these individuals. It's hard to get onto a stamp. And Armstrong is being lauded here for his invention of the FM system, which was 1939 is when it went public. And there's an FM radio in the back there. And, whoops, too fast. And then on the left here, the bottom left, is a vacuum tube. Vacuum tube is just a glass envelope that's been evacuated with a few electrodes in it. Basically a light bulb with an extra wire. And then to the right is a small transistor, showing you how the vacuum tube is being replaced by the transistor. Now we're going to start our story about the transistor in 1949, shortly after this device was invented. And this is the way the transistor was announced to the public. So it was on page 46 of the New York Times. It was not front page news. And it was on an article there. It's called The News of Radio. So radio was king. And TV was just starting in the 40s. And at the bottom, at the end of this article talking about things that are happening in the radio, is a little discussion here about a device, a new device that was invented. I'll read this. It says, a device called a transistor, which has several applications in radio, where a vacuum tube ordinarily is employed, was demonstrated for the first time yesterday at Bell Telephone Laboratories, 463 West Street, where it was invented. This is Bell Labs started in New York City, and then they moved to Murray Hill and Homedale. The device was demonstrated in a radio receiver, which contained none of the conventional tubes. It was also shown in a telephone system and in a television unit controlled by a receiver on a lower floor. In each case, the transistor was employed as an amplifier, although it is claimed that it also can be used as an oscillator in that it will create and send radio waves. And then it goes on. Now again, let's look at that transistor. It says, in the shape of a small metal cylinder, that's a small metal cylinder, about 1/2 inch long, the transistor contains no vacuum, grid, plates, or glass envelope to keep the air away. So the vacuum tube is what they're referring to there. Its action is instantaneous, there being no warm-up delay since no heat is developed as in a vacuum tube. A vacuum tube, you have to heat up the filament in order to have the thermionic emissions of electrons to make it work. So you have to, for those of you that remember the old-time radios, you had to wait for them to turn on. Right? Transistors come in, throw the switch, and immediately it's on. The working parts of the device consist solely of 2 fine wires that run down to a pinhead of solid semiconductor material soldered to a metal base. The substance on the metal base amplifies the current carried to it by one wire, and the other wire carries away the amplified current. Okay, so this idea of amplification is usually confusing to people. If you look at the early history of when Bardeen, Breton, and Schottky were trying to explain what a transistor was, they spent a lot of time trying to explain what amplification is. So I want to back up and look at amplification in the context of an electromagnetic relay, because this is really the model of all of modern electronic switches. So let's see what we have here. So let's first look at the illustration. Okay, so what you see, there are 2 circuits. There's a battery, and then there's a switch that's closing at the bottom here. This one at the bottom. And when that switch closes, current flows through the coil. and it magnetizes a piece of iron. And then that iron attracts that blue lever, which is made out of a ferromagnetic material, which is attached by a spring. And when it attracts it, so when you turn on the electromagnet, it pulls that lever down, and then it then allows current to flow from the other battery. Okay, so the lower circuit I would call the control circuit, and the outer circuit, the one with the light bulb in it, is the main circuit. And the key idea of this electromagnetic relay is that a small current, it doesn't take a very large current to throw that switch, but that can control a very large current in the device. So I would say that this is a device that amplifies current. Now you notice that the relay itself doesn't have the current. You have to have a power source. Okay, so all it's doing is a small current turns a switch, which then would allow a large current to flow. So the idea of the relay was invented, as I said, by Joseph Henry in 1831, and it was really put to use by Samuel Morse, who used it as a telegraph repeater. And I think I have a little demonstration of that. Okay, so what I'm going to show you, I'll bring up my camera here for a second. We're going to take a look at a Western Union telegraph relay. So this is a relay from about 1880. Let's see if I can find my... Okay, so here is, let's see if I can get a little closer. So here is the relay. I should have... Is there a laser pointer by any chance, or a stick? Or, oh, maybe there is. No, that's a pencil. Oh, I usually have a stick. Okay, so actually I can point to the object here. So what we have here are, these are two coils. That's okay, well, I'll point here. So there are two coils, these are the electromagnetic coils. And when I close the coil, what you should look at is this little piece that moves back and forth there. See that? And so I'm going to hook it up to a little... You see that moving? Okay, so when I energize the coil, it attracts the metal plate, and then it makes a little contact. And then the idea of using this as a telegraph repeater, I have another Western Union device. It's a Western Union sounder, which is here. I'm going to plug this on. You hear that go click? Okay, and so now I think if this works... Oh, thank you. Thank you very much. I'll use that in a minute. So this is a telegraph sounder here. And if you look at the sounder, so the sounder, the action is happening right here. That's what's making the click. And this box that it's sitting in is a little resonator box. It makes the sound appear louder. So what I'm doing is I'm using one circuit to control another circuit. And then the idea of a telegraph repeater is that you would have, you could have a telegraph key and then a distance sounder. But suppose you could send a signal 100 miles, but you wanted to go across country. So what you could do is you could station people every 100 miles, and they would listen to a message and then repeat the message, and then keep on doing it. Right? Or alternatively, you could take one of these relays and put it every 100 miles with its own battery, and then you could, one person in New York City could communicate with somebody in San Francisco, okay, with using this automatic repeater. So telegraph repeaters are sort of the beginnings of these early relays. Okay, so that's the idea of amplification. Okay, so now, another part of the origin is the use of the crystal diode. So cat's whisker diode, it's called. These are special kinds of diodes. A diode has two odes, an anode and a cathode, and it's a one-way valve for current. It lets current go in one direction and not another. The arrow in the diode symbol indicates the direction of positive current. It's a one-way valve. And these are metal semiconductor diodes. They're called cat's whisker. You can imagine a cat's whisker is kind of stiff, so there's a little tiny wire and it touches a metal crystal. So that's a cat's whisker diode. These are originally were made out of galena crystals, which is from Galena, Pennsylvania, actually. They're lead sulfide crystals, and they have this property that they allow current to go in one direction, not the other. And these were used in the early days of radio as detectors. So here you see these are the very simple radios. There's an antenna, a transformer, a tuned circuit, this device that lets current go in only one direction, not the other, a capacitor that stores, smooths out the signal, and then a set of headphones. That's a very simple radio. These are the kinds of radios that Cub Scouts frequently will make. And this dates back to about 1906. That's the beginning of real radio transmission. An improvement upon this, though, was going to the vacuum triode. So the vacuum triode used one of those glass envelopes, and now instead of having 2 odes, it has 3 odes. So one of them is the cathode and the anode, and then a grid is the 3rd ode. And in this particular one, because you put this resistor in here, the function of this triode is that it acts as a one-way valve as it does up here. Notice, by the way, the rest of this is the same. So here's a tuned circuit, here's an antenna, we have an extra capacitor here, we have this extra resistor, here's our headphone. Notice we have 2 batteries. So the batteries are giving you extra power. And what this circuit allows you to do is both have that one-way direction of flow, but also amplification. So the amplification and the power source is this battery, the B battery. So it makes it sound louder. So it acts as, the problem with crystal radio is very hard to hear a signal. With a vacuum triode radio, it's easy to hear a signal. And then it brings us to the point contact transistor. This is in 1948. And what we see here is instead of using lead sulfide as the crystal, it's using germanium. It's a semiconductor material. It's right here. And there are 2 wires that are just jammed into it. So instead of having 1 whisker, it's got 2 whiskers. They're right next to each other. And that was, so it's a germanium crystal with 2 whiskers. And again, we have current comes in, and then it comes out, and then the voltage on the base, which is the same as the voltage on the crystal, is what will change, is the control. And there's a current flow that will allow you to have this thing turn on and turn off. And so that was 1948. Here's an image of the Electronics magazine, September. The work was done in about June of 1948. Here's in September of 48. We have Bardeen over here, Bretan, and of course the manager getting all the credit here. William Shockley is at their apparatus. Bardeen did all the calculations for it. Bretan did all the building of it. And notice they call it revolutionary amplifier, the crystal triode. And so the category of the people there, we have Bardeen's the scientist, Bretan's the engineer, Shockley's the manager. And here we have a stamp in which Bardeen was honored, the famous American scientist's stamp. This was a stamp that was actually issued in Princeton, New Jersey. If you know when this came out, it was, I talked to the local post office over in Palmer Square, and they said, oh, they remembered the first day of issues, they were stamping the first day of issues stamp. And here we have the symbol of the transistor with John Bardeen. The uses of the transistor, it was initially used for hearing aids. So it was small, it would be an amplifier. It worked as opposed to just being an on-off switch. It acted as a linear amplifier. So you could amplify sound. It was used in transistor radios. Telephone repeaters. So just like the telegraph repeater, you needed to have telephone repeaters. That was the first application, major application of the triode. And then the transistor, the same thing. You need to amplify your signals on the telephone line. It's used as an on-off switch for motors. But the crossbar switch is for telephone switching. So that replaced the switchboard at the phone company. It could be used as oscillators, logic gates, and digital memory. And the digital memory is one I have a little demonstration I want to do right now of a flip-flop made out of 2 transistors. So let's just take a look at that. So I'm going to come over here, and let's see if I can do this well. Oh, this might not show up. All right, let's see if I can do this. So I have two transistors here wired up in a flip-flop. If you look very closely, this light, let's see if I can do this a little bit better. One of those lights is illuminated. That's that one here. Let's see if I can turn this all the way around. Let's see if this shows up a little bit better. Ah, you can see it now. Okay, so if you, this little transistor circuit, there are two transistors here. They're cross-wired as a flip-flop. This is a memory cell using transistors. This light is hooked up to one transistor. This other light is hooked up to the other transistor. They're cross-wired. And I'm going to go here and change the state of that. So this is a device that, as long as it's powered, it holds the state. Okay, and you might call this state, let's say, the zero state. So, and this is the opposite of that. And then I'm going to flip the state by just touching the wire here. Whoops, got to hit it in the right place. Okay, did you see it flip? Okay, and then I'll flip back. Okay, so I can flip back and forth if I hit the right wire and have my eyeglasses on. So it's so that's the idea of a flip-flop. So two transistors is all it takes to make a flip-flop. The reason I show it to you at this point is that one of the objects that we use in a computer is a memory. So let's take a look at that. So we're done with transistors now, let's go to the computer. So what is it? It's a machine for computation and processing of data manipulation. It's also, I would describe it as a programmable decision. So that's one of the things you can do with computers. Key people, John von Neumann. How is it used? This is a historical table. So solving differential equations is very important. Making tables for ordnance, for pointing with guns. This is actually battleships in World War II. You need to point your guns, you launch a shell 2 miles, and you needed to know about the weather, and you needed to know about the temperature and the wind to be able to figure out where the shell would land. So that was a very early application of computing. And of course, you're dealing with nerds that put these things together, so there's going to be games. And that was actually one of the early motivators. Later on, some of us remember the days of the IBM word processor. Started out word processing in the office machine and database management. And then also, for those of us in the laboratory, we use these things for data acquisition and control of instruments. The origins of this are the analog computer and the Turing machine. I'll get to those in a second. And its significance, as I say here, is artificial intelligence, as opposed to natural stupidity. So the story we're going to start is with Vannevar Bush. This is an MIT. And here he is looking at a piece of equipment. It's his differential analyzer. This is often traced as the beginning of the modern computer. There are earlier mechanical computers, but this one is really the important one. And it's a solver of systems of differential equations. And the problem that he was solving was the electrical power grid. And it was putting electrical signals out, bringing power to a distance, and also bringing telephone signals to a distance. So here, this is an image that we use in our course. This is a power plant in West Virginia, and there's a lattice tower here, and this is a coal-fired power plant, and it's sending electricity actually to New Jersey. And the idea is when you turn on the power, you have to worry about the power getting to the lines. There's inductance, capacitance, and it's in order to figure out that you don't get spikes and how power is distributed on a grid, you've got to do some very complicated calculations, and that's what he was using his differential analyzer for. By the way, this was motivated by industry. So this is General Electric with electric power and Bell Telephone. And it was funded by philanthropy. So it was the Rockefeller Foundation that funded Vannevar Bush. So this is really the role of economics. By the way, Vannevar Bush goes off, and he was FDR's science advisor in World War II, and was really the one that was responsible, a position paper that started the National Science Foundation. So a demonstration, a mechanical analog computer. I brought one of these with me. I had some students make one of these. Let's get my image on here. So just to see how this works. So by the way I find out about these things is to build them. it's very hard to read a paper and get all the details of this out of here. This is a device made out of Kinects. I'll get it running for a second and I'll tell you what it's doing. So it's got a okay, right now I'm running time backwards. So this is an exponentially growing solution. I'm going to get it into position and then I'll explain. Okay, so what this device is going to solve, it'll solve this differential equation. So I have a graph here. So let's see if we can get this on the screen. So this is a first order differential equation. This is the population problem for, imagine that we had everybody in this room blindfolded and we had one door and you were wandering around the room randomly and then eventually you would go and find the door. And then if you counted the number of people over time, the number of people would decay exponentially. Okay, and the equation that describes that is the first order equation. It's dy dt is equal to minus alpha y. Alpha, that parameter, is the size of the door. It's a bigger door, you decay away more rapidly. And this result here was a result obtained with this mechanical analog computer. And what the mechanical analog computer does, and I'll turn it on, is the information is coded in the rotation of a shaft. And this is a shaft encoder. So if I rotate the shaft clockwise, I'm getting a positive value. If I rotate counterclockwise, I'm getting a negative value. If I go 10 degrees, it's 360 degrees, 1 revolution. 720 degrees is 2 revolutions. So I can grow as a linear variable, a continuous variable, either positive or negative. And then when I turn this guy on, if I go in the right direction, I think I'm going in the right direction now, yes. So the wheel here in the middle, there's that red disc, and then notice that there's a wheel that's running on it, and it's getting closer and closer to the center as time goes on. But the rate at which it goes to the center slows down as I get closer to the middle. Okay, and this is using gears to actually program up this computer. So this is the beginnings of how one solved these differential equations mechanically. The date there is 1931. Okay, so that's mechanical solutions. Now let's come to Princeton. Actually, let's come to Alan Turing. We see that he was in Princeton here as a grad student, but he did some work in Britain before he came up with this idea of a Turing machine. So he comes to study with Alonzo Church, who's a professor of mathematics, in 36, and then they work together for a few years, and then he goes back to Britain. And so the story of the modern computer is the story of the Turing machine, John von Neumann's ideas of the stored computer idea, we'll get to in a minute, and the ENIAC computer, which is a pen. So let's spend a few minutes on what is a Turing machine. So the Turing machine is not a real machine, as it says there, but it's a concept of a way to process data using a memory tape. The key idea of the Turing introduced is the idea of memory. So prior to that, it's a state machine with memory. And we'll see how he does the memory. And what he does is he conceives of different ways of solving various problems. And it says processing data is similar to processing food. So you can think about the way you make a cake. Right? You have ingredients, you have a recipe, and you produce your cake. So in the case of a computer, you have an input, that would be your ingredients. The recipe is the programming, and then the output is the cake. And so this is the way it's done with a Turing machine. So you have a state table. We'll see how this works in a second. And the information is stored on a tape. And these boxes in the tape store anything. So it could be letters of the alphabet. It could be the intensity of light. It could be a number, a symbol. And all action happens in the red box. And if you look at the state table, what it has is it reads a value. Next would be the next state. It writes, so if it reads something, it will then write it, and then it moves the tape. So these are the 5 ideas associated with the Turing machine. So here we have our step-by-step instructions. This is the recipe. We have an action window, and then the ingredients get put into the tape initially. And then when you're done, you've processed it, and the products are there. So I have an example that we're going to do here. So here's an example where what you might put in the tape would be the intensity. This is a picture here of somebody's eye, right? And we see that there are boxes of different intensities. There's dark, lighter, lighter, so on. So that might be what's in every box. So that you could put in on the tape, you could put the intensity low. Or you could put, if it's a book, you could put the letters of the book. Or if it's a picture, the pixels, or equation numbers, and so on. Put anything you want on the tape. And so what we're going to do here is we're going to go through a little example. I'm going to run it in a second. And this is, we're going to load the data on the tape. This is BAB. Okay? And what we're going to do is we're going to load a program into the state table. This is the whole program. And what this one does is going to check whether what's here is a palindrome. A palindrome is something that leads the same forward with that. And there are two results. The result is either yes or no. Okay? And so it's going to say, is it a palindrome or not, yes or no? And I said, begin program execution. So I have a little, I've prepared a little PowerPoint here associated with this. Well, let's let this run. So come up in just one sec. So this is going to run that, here we go. I think I go click and it's supposed to run over that. So we're going to watch this execute. So it's moving, and as it's moving, so it's what's here, what's picking up on the right there, what's in the box on the left, it's showing you the different states. It reads a value, it writes a value, it's moving the tape around, following according to what's been programmed into the state table. And in this case, BAB, this is a palindrome or not. And in this case, it's telling you that yes, indeed, it is. And I think it's going to continue. I think it's now, let's see if it keeps going. I think then I had another version of it that was BAA, and it comes out and says no. But I think you get the idea. So that's the idea of a Turing machine. And now back to John von Neumann. So he comes to the Institute for Advanced Study. Here's his biography. 2 PhDs, one in chemistry, one in math. He escapes Europe, as do a lot of people. He's one of a number of Hungarian Jews that are referred to as Martians. I don't know if you know about them, but others are Edward Teller, the inventor of the H-bomb, Theodor von Karman, the brilliant engineer, Leo Szilard, John von Neumann. Martian, they all came from, apparently they went to the same high school as well. So he's a math professor at Princeton and at the Institute. And then he was working with ENIAC. This is around the time of World War II. And the military, the U.S. Army Ordnance wanted to develop a set of tables to point guns. So here's an ENIAC computer, the electronic numerical integrator in computer. 18,000 vacuum tubes in this thing. That was used to figure out these tables. And the tables that they were figuring was bullets going through the air. So this is an image of a bullet going through a flame. And we see that this was motivated and funded by government. And it was a role where politics, the politics of public works leads to this development of the computer. And here are the two principals that were involved in the ENIAC computer. It's Prosper Eckert and John Mauchly. They developed the ENIAC in 1946. One is, Eckert is an engineer, Mauchly is a scientist, computer scientist. But John von Neumann then comes up with an improvement on it. And the improvement had to do with the way the program was stored in the computer. So, scientist and engineer. Here are the circuits, by the way. Take a look at those skirts. That's the styles. This is in the 40s, late 40s. The young lady on the left is holding one of the circuits from the ENIAC computer, and then the EDVAC had fewer vacuum tubes in it. But the key thing is the way it was programmed like that state tape on the Turing machine. So there was a patchboard, so every time you wanted to put in a program, you had to put in a bunch of wires. It's a mess. And then John von Neumann comes in and says, not only can you have your data in memory, but you could also have your program in memory. So that's John von Neumann's contribution in the EDVAC, as he said, let's put the program as well as the data in memory. And then also, this machine was a base 10 machine, so it was like a calculator. And the idea of John von Neumann and others was to use a binary computer. So he develops that as well. So he does this EDVAC report on the stored program computer, so he puts his program as data in the machine. Then he builds a computer at the Institute for Advanced Study, and he also is active in the Atomic Energy Commission. And here's the EDVAC report. So this was the U.S. Army Ordnance official government document. The only reference to John von Neumann is the acknowledgments at the beginning. Of course, John von Neumann wrote the report. So they say, acknowledgement should be made to Professor John von Neumann and Dr. Herman Goldstein. They worked together. Goldstein joined the project at the Institute, and the U.S. Army Ordnance Department was the funder. And here we see John von Neumann in front of the computer. The Institute for Advanced Study, as you know, is a theory, it's a think tank, right? But they had one experimental project, and this was their experimental project. They built the Institute computer, which I believe now is at the Smithsonian. Here's John von Neumann with it. And we see that the computer, the ENIAC computer, was based on the way we do our arithmetic. Whereas the Institute computer and used binary numbers, ones and zeros. And so here we see the same equation. This is 5 and 5 equals 10. This is 5 in binary. So this is the 2 to the 0s, that's the 1's column, the 2's column, the 4's column. So 101 is 4 plus 1 is 5. So that's 5 and 5, and that equals 10. Okay, 10, so that's 1/8. That column's the 8 column. The next one is the 4's column, so that's the 2 column, so 8 plus 2 is 10. So the demonstration here is a little binary counter that I've done out of kinetics. Oops. There we go. So let's just take a look at our binary counter. That actually fits on there pretty well. That just a little bit. Good. Okay, now let me get that little thing in front here out of the way. Okay, that's good. Okay, so we see this is the 2 to the 0s column. You'll see in a minute. I'm going to put some balls in it. It's data 2 to the 1, 2 to the 2, 2 to the 3. So this is a binary counter, and I'm going to use little balls in here. Okay, so you see that this has the value of 1. So it's 0, 0, 0, 1. See that? There's one ball there. Then I'm going to add in another ball. Okay, now it's 0, 0, 1, 0. And I'm going to add in another. That's 3, 0, 0, 1, 1. That's 4. Did we lose it? All right. I will go and drop it in again. There's 4. I just reloaded 4. There's 5. And now what I'm going to do, make this a little bit higher, this thing also will function as a binary adder. So I'm going to put 5 in at the top here. This kind of a device, but it's done with transistors, is in a modern computer. That's 1, 0, 0, 1. Okay, so I've got 5 on top. It's a little hard to see it. So I have a ball there and a ball there. So it's 0, 1, 0, 1. And I have 0, 1, 0, 1. And I put these two together. Okay, and my result is 8 plus 2, so that is 10. So this thing is functioning as both a... It's kind of cool. And the building block on this, the decision maker, is the same thing that you do electronically. It's a little flip-flop device. I'll get a little closer here. It's a little hard to see that. Later on, you can come up and take a look at it. But there's a little flip-flop. I'm flipping it back and forth. It's a two-state device. So it's a little lever. It's one state or the other state. So that's the flip-flop. And then that allows you to have the carry, and it does some kind of early decision making. So that's a mechanical a mechanical computer. Okay, back to Institute for Advanced Study. John J. Robert Oppenheimer was the director. By the way, there's another Princeton connection here, which is with Claude Shannon. So Claude Shannon got an honorary degree at Princeton in 1962, and he was a visitor at the Institute for Advanced Study at the same time that John von Neumann was there, and also at the same time that Turing was here. You can imagine what the Institute in Princeton was like in the 30s. I mean, it had all these really brilliant people. Claude Shannon was the one who took Boole's algebra, his binary algebra, and applied it to switches, to relays. Okay, so he made that link. And this is often referred to as the best master's thesis in history. It's called A Symbolic Analysis of Relay and Switching Circuits by Claude Shannon in 1936 at MIT. And this was his master's thesis. And then he went off and did his PhD in something really goofy. He actually he got into this eugenics movement, but then came back to his senses later. So that's. But Shannon also should get the on this binary the binary adder. You should think of Shannon. So here's John von Neumann with his EDVAC design, with the stored program computer, and here we see an image of Alan Turing on a stand with his theory of digital computing. Now, to complete the story, to get to modern computers, we have to think of the microcomputer. So the date is 1971. It's at Intel. We have Robert Noyce over here and Ted Hoff. Ted Hoff is the designer. So this is the entrepreneur, and this is the inventor of the Intel microcomputer. And it's 2,000 transistors. This was the first chip, computer on a chip. The date's 1971. Inventor plus entrepreneur. And then by 75, just a few years later, these microcomputers were going out to the world in general. And this homebrew computer club started up in Palo Alto. This is volume 2, I think it is. And it says computer clubs continue to form around the country. This is what happens when you have these microcomputers. And one of the early members of that club, this is a year later after this came out, is Steve Wozniak and Steve Jobs. They found the Apple Computer Company. There's their Apple computer, the Apple I. Again, inventor is Wozniak, and the entrepreneur is Jobs. Jobs was inspired by a number of successful technical and entrepreneurial people. So he started his company in a garage, and so did Hewlett and Packard. They started in the garage, as well as Henry Ford. These are inventors and entrepreneurs, successful ones. And then this is what happens when a nerd designs a computer logo. So you see, it's the Apple computer. Jobs was working on an apple orchard, right? And there's Isaac Newton, right? So the apple falls down, hits him on the head. And then he turns it over to the Madison Avenue types, the advertising types. And this is what happens. So you get an apple with a bite taken out of it. Now that's a nerd joke. Byte as in a byte is 8 bits is a byte. Okay, and just so that you don't think that I invented that, here is an ad from the Apple Computer Company, and it says byte, B-Y-T-E, into an apple. Okay, and this is their board that they developed. And then here's another image of it, and this board is based on the Princeton architecture, the one that John von Neumann developed. And what I'm going to do here now is I have a computer here. I teach another course besides my History of Engineering course. It's a course on microcomputers. And the computer that I have the students build is essentially, it's the same microprocessor. It's the Apple I computer, which I have running here. So if you look closely, so you can see that it's executing. Right now what it's doing is it's just rolling some bits. If you look at the display is top there, it's going over here, it's going 1248, 1248. So these are the low 4 bits, these are the high 4 bits. That's representing 8 bits of information. And it's just taking zeros with a 1 in it, and just moving it, shifting left, shifting left, shifting left. So it's executing this. And then what's here is a chip is representing the 6502 is the microprocessor. This is one type of memory. This is another type of memory. This is called the glue chips. It glues it together. This is the heart of the computer. It's a clock. And then there's an interface chip that allows you to get signals in and out. So this is almost identical to the original Apple I computer. And they're very easy to build. As I teach our undergraduates how to do that. Let's see. Okay, and it's based on the Princeton architecture. So the Princeton architecture has an address bus, a data bus, and then the program and the data are all stored in one memory. So that's what makes it a Princeton architecture. So let's finish up with the internet. Just a few slides on this. So we've done transistor, now we do the computer. So what is it? The internet is a set of rules for exchanging data. You may have heard the phrase TCP/IP. That was the Transmission Control Protocol Internet Protocol. A protocol is just a set of rules. Think of it as like the Constitution. The people who defined that protocol are Bob Kahn and Vincent Cerf. They were at Princeton just a few weeks ago, actually. It's to connect computers and devices for communications and commerce. And what are the origins? It's ARPANET, as I mentioned, Licklider. BitNet, that's, for those of you that know Ira Fuchs in this community. Ira's not here, is he? So Ira was the developer of BitNet. He was the one who started the computer center here at Princeton University. And then NSFNet followed. And then what's the significance? Well, we now have social networks. And here's my really important one. And it's also, the significance is TMI-Net. Now, what is TMI-Net? So TMI, too much information, right? And net, not enough thinking. So, okay, enough said. The network allows you to buy and sell online. Of course, there are a lot of Princetonians that connect to this. So one is Jeff Bezos. There he is. He made a fortune. Right? I was actually his freshman advisor. I wish when he was in my office, I asked him to invest some money for me. Electrical engineering and computer science major. Meg Whitman was an econ major. She started eBay. So again, these are things that couldn't have happened without network computing. Whitman College at Princeton is the direct benefit of the computer funding. You can also ask where money comes from at Princeton. Forbes, it came from publishing. Right? Rockefeller came from oil. Right? Maddie College, that was Dean Maddie, that came from investments. Let's see. Butler, wow, Lee Butler actually was a car salesman. So that came from marketing. Wilson College, I think that came from politics. And then here's Bob Kahn getting an award with Vincent Cerf. And here's an image of what that TCP/IP is all about. So what happens is you have your computers that talk to a router, and then you go off on the internet to some distant machine. Okay? And so TCP/IP, it's the core of this layered network that allows you to send packets of information and then reconstruct. TCP exists at the two ends, and then the internet protocol allows you to send the packets to get them reconstructed. I'm not going to go into the details. Also, another Princetonian, Eric Schmidt with Google. Can we trust Google with our secrets? You know the answer to that one. And then also another Princeton connection here with the internet is David Boggs, and graduated as an undergraduate in 1972. And then the next year he goes and works with Bob Metcalf and invents the Ethernet. Okay, so 1 year out of Princeton, and he's there. He's one of the co-founders, one of the co-designers of the Ethernet. And here's an image of the Ethernet. So it's actually here. It's the wires that you use to connect your computer to your router. And the 10 base T, that's a 10 megahertz baseband network. Here's my symbolic slide for the computers, really, for this lecture. So this is a slide came out, it was issued at the 50th anniversary of ENIAC. ENIAC was 1946, this is 1996. And what we see here is a brain with some computer circuits in here, and this idea of artificial intelligence. And my last slide is just the idea, these are the people that I've highlighted. We have John Bardeen, of course, with the transistor, John von Neumann, the Hungarian stamp here, with the stored program computer. And then here at Princeton, just a week ago, over in Friends 101, we had Bob Kahn and Vinton Cerf talking about their contributions to the internet. Thanks very much. I'm sorry I went a few minutes over. Sure, okay, one in the back there.
How did the ENIAC to base 10 computations? Did it have something that held 10 states, or?
So I actually not delved into the circuitry. But first off, all circuits are available online, and a lot of these things are available. I believe that the computations, they were 10 digits. It was very cumbersome. I think it was modeled after an adding machine, and then they also had to figure out how to do integration in that. So I don't know the details of how they did it. But you can sort of get an idea of the complexity. It couldn't have been too bad. As I said, it had 18,000 tubes. Okay, so if we talked about a chip with 18,000 transistors, that's not a very complex chip. So I don't, it's easily understandable. I've just never looked at it. Yes?
So the third computer going next, what role are Princeton going to play?
Okay. So the question is, where are they going next? I can't answer that. But what role are Princeton people playing in it? A lot. So now, I talk to my pals in the computer science department and in electrical engineering. And I know that the next generation designs on the internet. So we're at Internet v4. That's, if the dotted notation, your IP protocol, you have 4 bytes of information. So like Princeton's address, 128.112.128.1. That's actually the largest number that you can have would be 256, that's an 8-bit number. So it's 8-bit, 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 8-bit. We're now at V6, and people at Princeton, that's like Kahn and Cerf talked about this. At V6, the problem is they ran out of addressability. It's kind of like having a post office with not enough boxes. So they've gone now to a new protocol, V6. Much more complicated protocol. The Princeton people played a central role in that. Our networking, our people are very well connected. And where they're going, so, ultimately people look at the brain. Right? As a matter of fact, John von Neumann is very interested in the capacity of the brain. And I think we're still a long, long way off to duplicating the brain. People talk about matching the number of neurons, but the neurons processing is more an analog processing than the digital processing. So it's not, you can't just count the number of neurons and say those are the number of operations. It's much more complicated. It's also not even clear, from what I know about neuroscience, that all the computation is done in neurons, at the synapses. There are a lot of other places, also in chemistry. So I think that ultimately it would be to solve these very difficult problems, which are bigger and bigger computers. There is something that I did dabble with for a number of years, which is quantum computing. And these are analog computers, using atoms as basically storing information in terms of the phase of spin of quantum particle. And the problem with analog computers, the reason I sort of got away from that, is analog computers lose precision over time. Now, I don't work in the area, and people that are in the area say that there are some very clever algorithms to correct the errors. And if that happens, then we might have some sort of whole new generation of computing. But as it stands right now, that's sort of the topic of interesting research. And then that is going on by the MITRE Corporation right now in our plasma physics lab. So there is a group, maybe anybody here from MITRE? No one's here from MITRE. There's a group doing quantum computation over at the plasma physics lab. And then we have 2 faculty members, Andrew Hout and Jason Pedder, over in physics. Hout's over in electrical engineering, whose focus is quantum computation. Oh, there's another fellow to it, and we have. So that's, I think, in the future. Any other? Okay. Last question, Barbara. Yes?
How long would it have taken for that transmission when
just asked so the issue is how long does it take for a relay to throw? Okay, that's actually something in the course that I do on microcomputer controller toy training. We actually go and pull out an oscilloscope and measure it. So it depends upon the strength of the spring and the strength of the magnet, but it's typically many milliseconds. So if you had 100 switches in a row, okay, it might be a second for that switch to throw. So it can limit the bandwidth, the information rate that you can send through. And this is also a reason for high-speed switching if you want to have very short switching time. So with a transistor, you can get switching times of less than a picosecond. Okay, so 10 to the minus 12 seconds. So this, again, another advantage of using a transistor as opposed to mechanical relay. Okay.
Okay, I think, thank you very much. This year, you know, I think there's a little bit of, which is a t-shirt, which I know you need.
Yes, sure.